Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we learned about the counter type ADC, and we have seen that in this ADC, every time the new conversion starts, then the counter used to get reset. That means for the every new conversion, the counter starts from 0 onwards. And that is the biggest drawback of this ADC. Because even if there is a no change or a very small change in the input signal, then also the counter starts from the 0 onwards. And due to that, this type of ADC is very slow. So every time, instead of starting from 0, if the counter goes either up or down based on the change in the input signal, then the conversion time would be much faster. And exactly the same principle is used in the tracking type ADC. So now let us understand the working of this tracking type ADC. So as you can see, the schematic of this tracking type ADC is very similar to the counter type ADC. But here the counter is up down counter. So as you can see, the output of the counter is given to the DAC, and the output of the DAC is compared with the input voltage using the comparator. Now whenever this ADC is powered up, then the counter starts from 0 onwards. That means initially the output of the DAC will be equal to 0, and due to that the output of the comparator will be high. So whenever the output of the comparator is high, then the counter starts counting in the upward direction, and due to that the output of the DAC will increase gradually in the upward direction. Now whenever this VDAC is greater than the input voltage, at that time the output of the comparator will become low, and due to that now the counter starts counting in the reverse direction. And once again, whenever this VDAC is less than the input voltage, then the comparator output will become high, and once again now the counter starts counting in the upward direction. So here, instead of starting from 0, the counter goes up or down according to the input voltage, and hence the ADC continuously keeps track of the input voltage, and therefore this ADC is known as the tracking type ADC. So here the output of the counter can be latched whenever there is a transition in the comparator output. That means whenever the comparator output goes from either high to low or low to high, then the output of the binary counter can be latched. And if you see the typical conversion pattern of this tracking type ADC, then it will look like this. So initially the output of the DAC will increase continuously until it reaches the input voltage, and then after it will track the input voltage. So in this case also, the maximum conversion time would be equal to 2 to the power n minus 1 times t clock. That means if the change in the input signal is equal to the full scale output voltage of the DAC, then the counter will go from either all zeros to all ones or from all ones to all zeros. And for that, the counter will require total 2 to the power n minus 1 clocks. So we can say that the maximum conversion time would be equal to 2 to the power n minus 1 times t clock. But if you see the average conversion time, then it would be lesser than the counter type ADC. Now for any ADC, this conversion time is very important parameter because it decides the sampling time of the ADC. That means the time after which the input signal will get sampled. So in general, for any ADC, the sampling time will be equal to the conversion time plus some additional delay. And for the tracking type ADC, this conversion time depends on how fast the input signal changes. That means if the signal changes very rapidly, then the ADC will take more time for tracking the input signal, and hence the conversion time would be more. On the other hand, if the signal is changing very slowly, then the conversion time would be less. So basically, for this tracking type ADC, the conversion time depends on how fast the input signal is changing. And not only for this tracking type ADC, but for the dual slope as well as for the counter type ADC, the conversion time depends on the input voltage. That means for the given resolution and the given clock frequency, the conversion time for all these ADCs depends on the input voltage. But if we want to sample the input signal at the uniform time interval, then we should consider the maximum conversion time of the ADC. So if we consider no additional delay in the ADC, then for the uniform sampling, the sampling interval should be equal to the maximum conversion time. And the sampling frequency or the sampling rate will be the inverse of this sampling interval. So for any ADC, if Fs is the sampling frequency, then the maximum allowable input signal frequency is equal to Fs by 2. Because according to the Nyquist sampling theorem, the sampling frequency should be at least 2 times the maximum input frequency. And for a moment, if we consider there is no additional delay in the ADC, then the maximum allowable input signal frequency is inversely proportional to the conversion time. So due to the large conversion time, these ADCs are very slow. And not only that, for these ADCs, the conversion time depends on the input signal. So in a such application where the signal is changing very rapidly, either a flash type or the successive approximation type of ADC is preferred, as they are much faster compared to all these ADCs. So in the upcoming videos we will learn more about them. So I hope in this video you understood the working of this tracking type ADC and why the conversion time of the ADC is very important parameter. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to this channel for more such videos.